move in solid, ions carry charge. You can say charge or current. So let's record them. C. The student investigates materials to use as inert electrodes in the electrolysis of the aqueous sodium chloride. Compare the materials A, B, C, and D, and their results are shown in the table. So you have A, B, C, and D. So A is soluble in water, conducts electricity, and it has a density of 7.87. B is no, and conducts electricity. Water has a density of 12.41. C is no, conducts only when molten, 2.17. D, soluble in water, does not conduct electricity, density of 1.54. So you want to explain the materials here. You want to explain the material which is going to be shown in the table. It's going to be used for electrolysis of the sodium chloride. So the material is going to be B. Inert electrode has to conduct electricity. Inert electrode has to remain solid. Electricity has to remain solid. Okay. So 21. The scientist uses chromatography at melting points to investigate the purity of 3 samples of a painkiller, so A, B, C, and the scientist compares the 3 samples with a pure sample of the painkiller, and then the scientist compares the melting and boiling points in the 3 samples to the pure substances. And so then this is a 6 marker. This is a chromatography question for a 6 marker, and if you want to get the highest marks, which is those AO3 marks, this is how you do it on like a sort of bullet point scale. So use the chromatogram and the melting points data to provide samples, and the C is pure, which contains the painkiller. Explain your answer. Okay. So the way that I would do this is okay, so what do we know about melting points and pure samples? We know that if a sample is pure, the melting point is going to be low, and the boiling point is going to be higher than normal. So the melting point is going to be lower than normal, and the boiling point is going to be higher than normal. And so the pure painkiller is 136, so we know that C is definitely the pure painkiller because it's right bang on 136. And we know that B is, again, B is too low, and it could potentially be it, but again, no, sorry, it's too low, so it couldn't be it. And then so it's not that one. And A potentially could be it because it is in the range. So it's most likely C could be A. And you'd want to list that down. So the first, so use chromatograph melting point to determine which sample A, B, and C are pure and which one contain the painkiller. So C is a pure sample because it has a specific melting point. So it has a specific melting point, which is the same as the. No, what would this be the same as? It has a specific melting point, which is the same as the melting point of the painkiller. B has a melting point too low to contain the painkiller. Okay, and then And then you'd move to the chromatography. Sample A has 2 spots. So, it is not pure. And sample B has 2 spots. So it won't be pure. Now if we look at the chromatography again, remember the only one that doesn't have a spot is C and the pure painkiller, and again they have the spots at the exact same places, which means that C is most likely the pure painkiller, and A is most likely to be the mixture of the painkiller because it contains the painkiller spot, so we should probably write that down. And A has a spot at the same RF value as the painkiller, and so A includes the painkiller in its mixture. And C is the pure painkiller, as it has no other spots, and its only spot